So we're going to finish up our work on centers of stuff. And so we've looked at composite parts. Now we're going to look at something where it doesn't lend itself to composite parts. So you need to use integration. So here we have a ubiquitous blob, all right, and the following is a differential mass within the blob, all right. So the basic equation we've had thus far was relative to x. The x center is the total weight, or the x center times the total weight equals the x center times the weight of the part. Okay? So you'd take all our parts, get their weights, find the x center of the individual parts, sum those all up together, divide by the total weight, and you would have the x center. Now, so look at this. This is just summing the total, all the weights of the parts. Well, if you have differential weights, small things, that would just be, integration just means sum. So summing up a whole bunch of small weights to get the total weight. No difference. This and that are the same equation. So instead of having a part that has some size to it, we have a part whose weight is differential, and you're simply saying where's the x coordinate of that part, because it's basically you're going to take a particle here, so the x coordinate of that particle will basically be it. All right. So, and now sum all them up. Now a key point here is when you see this x, what that's basically saying, because that x is a variable, you're going to let x move around as you do all these little differentials. It's basically saying that x is a variable. It says you need to integrate against it. So when you make your dw, the easiest way to use this equation is to come up with a differential weight where dx is part of the expression. All right, but if you look at this and compare this, it's the same equation. So x, center of mass or center of weight, and assuming this isn't something like Mount Everest, so you have gravity varying over that, it's we also have here the center of mass. They're all kind of the same thing. All right, so let's look at this. So here's our equation, xg equals x dw, integrate that over the integral of all the weight. If gravity is constant over this thing, then we can write gravity times differential mass would be differential weight. Cancel out the g's, and now we have xm. So same equation applies. Likewise, let's suppose we have constant density here, which would probably, rather than be this symbol, we'd rather use the rho. But same idea. So xg, which we know is equal to xm, if we had a constant density, we could factor density times differential volume would give us differential mass. So we can factor out the densities. And now we have xv. Just showing how we can go through the same basic equation. If our volume can be broken up, if it has a constant depth in one direction, so then we could express our volume as this constant, say, depth and differential area. Well, we can factor that out. So now we have x of a, same basic equation. Or maybe we have a constant differential area. So we'll factor out the a's, we'll have a differential, we'll integrate over a length instead. No problem. So these are, when we go to integrals, what we want to get across is we want to come up with, give it be it a differential mass, weight, volume, whatever, and basically this is the clue. Try to integrate against that, because this is a variable, but it's the same equation as this one. All right, so problem we're going to do next is this one. So what I have here is picture a hotel, okay, where some architect has designed a plate that hangs from the ceiling. It's a decorative plate. I'm going to adjust my field of view here a little bit. So this is a plate. So you've got a 90-degree angle on this side. It's 16 by 16 feet. And then it has this cut in it where along the top surface, so on this top edge, the equation would be y to the 1/2 plus x to the 1/2 equals 4. And you will not be able to go into any table and find this picture. Won't exist. All right. So because of that, we can't really break this up into composite parts. It's calling for integration. So for this, we have this plate that's going to hang from the ceiling. The specific weight of the plate, which is like density, is 180 pounds per cubic foot of this plate. The thickness of this plate is 1/4 foot, or 3 inches. And so what we want to find is the center of gravity of the plate. And then we want to figure out what is the tension in the chords. And if once you knew the tensions in the chords, then you could use knowing the tensions, you could design the chords to be able to support the weight of that plate up in the air. Now we'll note, given specific weight, if we know the volume of this plate, multiplied by this, we would get the total weight of the system. So in doing this, to get the tensions in the chords, we'd have to know where the center of gravity is, so we could apply the weight at that point, and then do a rigid body equilibrium problem to figure out the tensions and do everything. So this sets us up with our next chapter, which will be rigid body equilibrium. Now when we look at this, comparing the x and the y, it's symmetrical. So we know right away xm equals ym. So we only have to do this thing once. Now, so what am I going to do? I need to compute one of these. Well, hold on. Let me just divert for a second. This is a uniform thickness plate. So here we have, let's look at this. The coordinate system is on the top surface of the plate, and the plate thickness coming down is 1/4 foot. All right. So that tells us that the center of mass relative to z, if this is 1/4 foot, this is where the origin of the coordinate system is. Put a little O here. All right. The z center is half that down, or z equals minus 0.125, which is minus 1/8. So we need to do a computation, determine x or y, and then we immediately have the other. Because people always seem to want to work in x, and sometimes students they're so focused on I have to use x, and there's nothing in a variable, I'm going to use y just to be different. All right, so y sub m, so this center would be given by the following equation, y dv over dv. The density here is constant, so once I get volume, I can multiply by density to get mass, or specific weight to get weight. So when I get the center relative to volume, it'll be the same as the center of mass, or center of weight, or whatever you want to call it. All right, so here's the equation. Y is a variable, so it says I want to come up with a differential volume where I have a dy. Well, that's really easily done. So consider the following. So here I have, so this sliver here is meant to be a dy. Now relative to 16 feet, it's pretty big, but I can't draw that small, so just use your imagination. So I have this sliver, this is dy, okay, and so this will be my differential volume that I'm going to work with. It's 1/4 inch high, you know that. It's going to have some length here, but so what's going to happen is I'm going to, as I move these slivers down, all right, this will be some distance y. But then knowing that, I can plug that y in, and then I can compute x from this equation. All right, so here is a differential mass. Where is the y center? Right here, right in the middle of the dy. So I can let y go from 0 up to 16, where I just have these little differential masses or volumes going along. So I have the y, here's a dv, y is the center associated with that, and I'm just going to add all these things up. So I need to form a dv. So this is basically, if this is thin enough, this is just a little rectangular block. All right, so I have the height is 0.25. I'm going to have to get this distance x as a function of y, and then it's dy thick. So there's the volume, 0.25 x of y dy. Well, x is a function of y, that's right here. I have that right there. So that would leave me with 0.25, 16 minus 8, y to the 1/2 plus y. So for any given y, this equation will tell me where we are in x, dy for the thickness, and bam, we have a differential volume. So we just stick this in. Y for the center of mass, volume, weight, they're all the same. And people generally put a bar over this. It's not a vector, it's just a way of saying that it's the average. So we'll just let that be there. So y is going to move from 0 to 16. I have to put a y in. Boom. Now I put in differential volume. The whole expression. And then below, we just have differential volume. And there we have it. If you were to multiply this all out and integrate it and do all that stuff, which I'll let you do in your spare time because you're learning integration, so it's good practice. Let's see, this is top is 34.1325. The bottom works out to 10.67. That's important because what is this? Integrate dv. This is volume. All right, continuing, you get 3.2 feet. So that's y bar, x bar. So we now have, and we know z, where that is, put a little bar over that. And so we now know where the center of gravity is. Knowing this, we can get the weight. Weight is 180 times the volume, 10.67. That works out to 1,920 pounds. All right, so we have the weight. Now we can tackle the problem of what are the tensions. We need a little bit more room to work with. And so let me, let's see here. So if we went over some distance, 3.2, and that's 3.2 and down an eighth of an inch, let's suppose that's right here. We can go up here now. And I'll just put in 1,920 pounds. Here's the center of gravity. Okay, so we can see that. So this is now kind of like a free body diagram. Instead of having chords here, I have my tensions. Here's the weight. Let's go at it. Well, if I sum forces in the z, we're going to have minus 1920 down plus T1 plus T2 plus T3. So now and then we can look at this and go, note, okay, we have symmetry. We have symmetry from here to here with respect to the plates. So we'll note that T1 equals T3. Must be the case. All right. So even if I do that, I have one equation with two unknowns. Can't solve it. All right. So we need to come up with another equation. And here's the easy way to approach this. Let's take the moment about the x-axis. So here's the x-axis right here. All right. This tension and that tension here are on the x-axis, so they can't exert a moment. All right. This here's our center of gravity. Here's 1,920 pounds coming down. Here's this tension out here. Okay, so basically what we have is this tension, if it could do anything, would take us clockwise, counterclockwise, and this, the weight, is trying to drive the plate clockwise. So that would be a negative moment. And the two, obviously, there's enough tension, the tension is high enough that it'll counteract the moment of the weight. All right. So what we learned from the previous chapter is all that matters, all right, is the perpendicular distance. So this is going straight down. All that matters is the y distance over to here. Now this center of gravity is slightly below this line, so I'm trying to show that there. But that doesn't matter. All that matters is, because remember, we can move this up to the top surface. You can move a force along the line of action. So we can move it to the top surface, and then it would line right up with this. Doesn't matter. All right? So all we need is this distance along the y to get over to the x-axis, but we have that. It's 3.2. All right, so moving up slightly. This would take us clockwise, so that's minus 1920 times 3.2, and T3 is plus T3 times 16. All right, solve for T3. Come up with 384 pounds, which is equal to T1. Now that we have that, we substitute into here. So we have minus 1920 plus 384 plus T2, we don't know, plus 384. Solve for T2, come up with, moving that up, 1,152 pounds. All finished. So we have an example using integration to find where the center of mass is. For those that continue on to the dynamics course, you'll get a bit more of this next time. And then here we have the whole principle of rigid body equilibrium. The sum of the forces in any given direction must be 0. The sum of the moments must be 0. And you can take the moment any place you want. I took it along the x-axis. So that finishes up Chapter 9. It introduces Chapter 5, and we will continue on. Catch you soon. Bye.